I decided to actually maybe also include dark matter, and in particular, a model I've been working on, which has a coupled dark matter, dark energy model. Sorry? And regular matter, yeah. So matter, so we can also. So this one will be more like string motivated model. So let me then just start up with, reminding ourselves what is the concordance lambda CDM model, which is a phenomenological model, cosmological model, where in which, well, it's supported by observations, and in this model, a huge part of what we call the cosmic pie, essentially 95%, constitutes the dark sector, which is the subject of this workshop. And part of it comes in the form of what we call dark energy, whatever is causing the universe to accelerate today. And about 27% is dark matter, which is, again, some kind of matter. We don't know what it is. And, well, it is also complemented by with the inflationary scenario to account for the structures that we observe today. And in particular, in terms of dark energy, observations seem to be so far consistent with tiny cosmological constants, so a tiny constant energy density, which will drive the expansion of the universe. In particular, the energy density having this tiny value, and the equation of state being very close to -1, so indeed accelerating. And we know that further future dark energy surveys will tell us more about, we prove this equation of state, and hopefully we'll learn something more. So from the observational point of view, it seems, things are coming, even if apparently a cosmological constant is still okay and consistent. And but probably you have heard, all of you have heard of various hints at perhaps new physics, perhaps not, beyond lambda CDM model. For example, the measurements of the Hubble parameter from direct and indirect, the inferred value from the CMB observations, which seem to be, important. And, this is still topic of discussion, but maybe it is indicating some physics beyond standard model, which may be in the form of some exotic dark matter, dark radiation, dark matter decay, coupled dark matter, dark energy, and so on and so forth. On the other hand, I'm sure everyone has heard about the recent theoretical constraints on the low energy effective theories of gravity, which will apparently, if true, these all come in the form of conjectures so far, so there's no proof, it's just conjectures, but in particular, they will rule out, if true, they will rule out a constant energy density in any theory that is consistent and has ultraviolet completion, for example, such as string theory. So this comes with the name of the SWAMPLAND conjectures, and basically what people are saying, what are the theories that belong to the landscapes, that is the set of theories that are consistent with a UV completion, and those which are not. Apparently, a pure cosmological constant will be here in the SWAMPLAND, if true. So I'm not going to discuss SWAMPLAND conjectures, so we can talk about during the workshop. But in particular, I'm just going to mention what is called the Sitter-SWAMPLAND conjecture says. Again, there's no proof. There's some kind of way to derive it in this last paper, but there's no proof. So the idea is that, the proposal is that the scalar potential in a low energy effective theory that is consistent with quantum gravity should satisfy either this condition or this. Now, originally, only this condition was satisfied, but quickly, these proposers realized that this clearly it's a bit too constrained, so it was refined to say that either the scalar potential satisfies this condition or this one. So this mean of this matrix is the minimal eigenvalue of this matrix, which has to be negative, sufficiently negative. So clearly, these conditions together, either this or that, excludes the Sitter metastable de Sitter vacua, but of course, sufficiently unstable de Sitter are perfectly fine, if true. And also in particular, because this constancy, which again haven't been computed, are supposed to be numbers of order 1. And now this I here corresponds or runs over all of the scalars present in your theory. So this again, in trying to make sense of this conjecture, people also have been related this to other conjectures. So I just comment that, but I won't go into any more detail about those. So this is, I just wanted to put the status of this cosmological constant in there from the theoretical point of view.
Why does it lose out metastable
Why? This allows only for unstable. So essentially the Hessian for a stable, beta stable has to be all positive. Mm-hmm. So this is the minimal eigenvalue, has to be sufficiently negative. And the units are correct. Potential has units mass to the 4. Derivatives with respect to the scalar has mass, and so I hope the units are correct. So this is mass to the 4, and then there are two scalar derivatives. Maybe the derivative with respect to scalar fields. Yeah, so these are derivative with respect to the scalar fields.
But any scalar field?
All of your scalar fields in your theory.
But the Higgs included?
If the Higgs is included.
So the Higgs is irrelevant, because the Higgs already...
That's why we have this and not just that one. Exactly.
The second one, there should be some moduli that is the minimal, minimal element. That,
yeah. Okay. So sufficiently. I mean, there can be maxima, but not minima in that sense. Yeah.
When you say unstable de Sitter, you mean that there is
a maximum. That's so Minkowski, supersymmetric Minkowski are fine. Supersymmetric anti-de Sitter may be okay. So you may have, indeed, if you may have a supersymmetric Minkowski, and then your maximum, which is consistent, and then a runaway. That will be typical, no? Or even anti-de Sitter, maximum, and then go away. So indeed, I mean, it was very quickly realized that this is kind of the obvious thing you can have, so that's why this condition alone is a bit, I mean, people realize also because of the Higgs that this is not possible. Okay, so again, conjectures. So, but what does this imply for dark energy? Well, this is interesting, whether it's correct or not, but also in view of cosmological observations, it's interesting to ask. And so here I also want to ask, to mention that, of course, people have been considering dynamical dark energy since many years ago, so now maybe it's more relevant. So rather than having something which will be, this is supposed to be just a tiny cosmological constant, which will be excluded if we sort of want to accept those conjectures, will be ruled out. So this will either have to go down or be a Minkowski, whereas some maxima are allowed as well as some runaway. Or we just think of something that looks like this, and maybe when scalar field is rolling down, this is what is causing the accelerated universe. So it seems that quintessence now may be more interesting than ever. And when the first version of the conjecture was proposed, these people came with some bounds from cosmological observations, very conservative bounds on this constant C, which already we see is not exactly 1. And, but once you relax, of course, this single condition, and you have either one or the other one. So in other words, allowing for the CITER maximum, then it is possible, as I will show you, to then have both constants of order 1 and an equation of state that gives me an accelerated expansion. But the price to pay, not surprisingly, is that you have to fine-tune your initial conditions. So how much do we have to fine-tune? We'll see. So I'm going to discuss a model we proposed in terms of what will be the simplest kind of situation you may have in a string theory setup, and which is what we call runaway quintessence from a string modulus. So this is very, very simple, and I will discuss what are the problems and what things look good. And then hopefully I will have time to discuss these couple dark energy, dark matter models, in particular for two periods in the universe evolution, early universe and late time cosmology, and also included just matter, matter or dark matter. So hopefully I'll have time. And then I'll include a summary at various stages. Yeah, I have time. Yeah, but I may get a bit long. Okay. So let me start from quintessence point of view. So what do we need to try to explain the accelerated expansion of the universe today? Well, we need a slowly rolling ultralight string modulus if we are talking about string setup. In other words, the wave of the scalar potential today has to have this value, a very small value, and the mass also needs to be very, very small. So indeed, this already is telling us that we require two fine-tuning. So if we look carefully, of course, many of the problems that arise in finding.
The origin of the bound on the mass?
Because the Hubble constants, essentially, you want a field, Hubble constant today, you want a field that is lighter than h, you get there. Mm-hmm. So you are fixing, first of all, the size of the V, and then you also fix the mass. So yeah, many of the ingredients that arise when you are trying to build the CITER vacua in string theory also appear when you are trying to do quintessence, but I would say that actually we have a little bit more problems. So in particular, well, usually when you look at string theory, what happens is that a string dilaton, for example, or a volume modulus may lead to fit forces and the varying of fundamental constants, and this has been discussed since long ago as well. You may try to evade this by looking at local modulus that may be sequestered. So sequestering is something key that you will need, such that the couplings are weaker than standard model couplings. And another option that has also been discussed in the past is that the quintessence may just be an axion, and therefore you may evade some of these problems with fit forces, and it can be easily light because the masses usually are suppressed. However, the problem in that case is that the decay constant needs to be super Planckian, and again, in terms of these quantum gravity constraints, it seems that this is, it's not possible very easily, or it's hard at least. So again, it presents some problems. So I just present here some list of very recent papers that discuss quintessence models recently, and then I will, and I will present something that we call a super simple model which in principle has some theoretical control, and we'll see that still, so the issue is that we require a fine-tuning, which you may or may not want to try to explain via anthropic principle. So what we do is just simply consider an early universe scenario where, say, inflation ends in a supersymmetric Minkowski minimum, where most of the moduli are stabilized and heavy in an n equals 1 supergravity framework. So that means that these two conditions are satisfied for, say, most of your fields, scalar fields, where these fields here in this language are complex superfields. And
why do I end in a supersymmetry?
That we don't want to know. What we want is something that we know it's perfectly fine and we have control. And supersymmetric Minkowski is a good. So we start good. Yeah, it's a toy model, and we start with something that we can control. Say, a Minkowski SUSY is the most controllable thing we can think of. So let's see where we get with this assumption. And now we assume, for simplicity, that there is a single flat direction, say phi, well, another one, with these two components, a real part, which may be a string coupling constant, for example, or this axion, and theta, which is its axion. So the typical Keller potential for this field will take this form. And for example, for n equals 3, this could be an overall modulus. But there are other possibilities. For example, n equals 1 will be for other volume moduli, complex structure, dilaton, or blob moduli. So in particular, we want to look at what happens when n is equal to 1 and look at the kind of potential that we get. So first of all, the potential, so we say we start with this supersymmetric Minkowski, and in principle, the W for this flat direction, if it's flat, the W is protected and does not get perturbative corrections. So both essentially, it can depend on the real and imaginary part, but it does receive non-perturbative corrections, which usually go take this form. So W will take these kind of corrections for the flat direction, and on the other hand, the Keller potential may indeed get perturbative corrections, but as soon as we keep W equals 0, this hopefully will not lift the flat direction. So what do we want to start with? The simplest thing, as I said, is consider Keller some modulus phi with this Keller potential and the non-perturbative potential at leading order. Of course, there will be subleading non-perturbative corrections, which will be suppressed with respect to this one. So I will comment on the further corrections. And these, for example, may be generated by different mechanisms, worldsheet instantons, Gaussian condensation, or bulk of the brane, Euclidean branes, and so on. So basically, in this kind of pictures, both parameters, alpha and A, are model dependent. So this will depend on your model once you build it. And this constant in particular may itself be exponentially suppressed or not. And because it may just depend on the moduli waves of some other moduli. And this is just an example given by one loop threshold corrections. But essentially, those will depend on your specific model. So we consider simply just taking these two pieces for the moment at leading order. Compute the potential for the whole of the scalar field. And well, you can check that the potential does not depend on the axion. So the axionic part remains flat. It only depends on this axion, this phi. And again, this will be at leading order. Subleading non-perturbative corrections will lift this axion, and we will see what happens in that case. So this is so. No, because it can depend, so that's the point. It can depend on other moduli waves. So it's really, you will really need to compute which fields you have there. And we'll see that, of course, if we want to use this for quintessence, we need a specific value. So here is where one of the fine-tunings will come into place. So you can check that the potential takes this form. So this is perfectly fine with the SWAMPLAND conjectures. There's a de Sitter maximum, which is fine, and then there's a runaway, which is typical again. So in particular, so this is for n equals 1. And in particular, the maximum is located at this point and is consistent with the SWAMPLAND conjectures, the Sitter-SWAMPLAND conjecture. These corrections will be, again, subleading. And remember that we want to start from a Minkowski supersymmetric vacuum, which is something we have control of. And what's interesting here is that once you give up having the Sitter minimum to explain the current acceleration, having a cosmological constant, then at least one bonus is that you don't need to fine-tune perturbative and non-perturbative corrections against each other to achieve such a minimum. Of course, we will need to fine-tune because we want to explain the current acceleration.
That is probably very clear, but where do I see that the competition between perturbative?
No, here there's no, because we don't impose that we want this minimum. In the original, say, KKLT, you need a competition, or the large volume scenario, you compete with one another such that you get your minimum. But here, in principle, is fine.
How do you fix the initial conditions?
Yeah, this is another point. Let's see. Now, initial conditions are also important. I'm going to those because those are crucial too. So clearly, let's just look at the picture. Okay, maybe we may start somewhere here, or we may start somewhere here. And did we get there? Somehow. But it's also, it depends, the evolution will depend on where you are along the potential as well. So let's see what happens in particular. So, okay, we solve the cosmological equations. We want to see that whether this kind of simple potential can drive some accelerated expansion today with a correct energy density and equation of state. So these are the equations that you have to solve, and we have included the evolution since radiation through matter domination through today. So basically, this is a standard scenario of slow roll quintessence model where you have to impose the usual condition that the velocity of this is actually the canonically normalized field, and here I'm remember that the axionic part essentially is a flat direction, so basically this will come only with this field phi, canonically normalized. So the condition in terms of the non-canonically normalized field phi ends up being a condition on the potential, of course, compared to the Hubble expansion rate.
And this metric and affine connections are in some moduli space?
So yes, sorry, yeah. Of course, so this metric is in the modular space. So in this case, it's very simple because, yeah, essentially it's here, yeah. So in this case, it's coming from the Keller potential, which depends only on the real part that is on this phi. So essentially, these gammas, they all go like 1/phi.
So your extraction is the quintessence field.
The extraction is going to be my quintessence, and the axiom for the moment is a flat direction. I will mention what happens when I add subleading correctness. Very good.
I'm sorry for asking again, but you have a differential equation, but for the initial conditions, what are you?
Could you repeat the question?
He wanted to know about the initial conditions, so now I go to initial conditions because those will also be important, right? So, okay, so this is what we need. So, and we also can sort of look at what happens at this parameter that I want as a slow roll parameter at different regions in the potential that are interesting. So as phi goes to 0, of course, this is not interesting, and this parameter goes like this. So this side of the potential clearly is not interesting for us. But we can look at the evolution as we go towards the maximum, and then as we go towards infinity. So one idea that was proposed also since long time ago is quintessence at the tail, which means, well, of course, you have to go farther away. And obvious question is where we can source quintessence when we go to the tail of this particular potential. So either at both of these points, either at the hilltop, which is here, the maximum, or at the tail, which is somewhere here, while the Hubble parameter is large, the field will remain frozen. In particular, when the field is exactly at the maximum, it will behave as a cosmological constant for a long time until it starts rolling down. So we'll see how long it behaves. So it may just start to roll down in the future and we will never see it. But then the question is...
roll down towards the tail or towards the...
Oh, yeah, of course. Yeah, exactly, yes. Of course. Well, as soon as we are not there to be there... As long as as long as it's in the future, we don't care. So, yeah. So in principle, it will look like either the maximum or the tail are good for quintessence. And, well, this I already said, as soon as the condition is violated, the field will start to roll down in either of these points. But now I can define this parameter epsilon q, which, well, we can compare to h, or essentially we want to see that this parameter is small. This is low roll condition. And we want, of course, that there is quintessence, that is that the Hubble parameter is dominated by the potential energy. And you can check that at the tail, when phi goes to infinity, this parameter behaves like this, which which is clear that then the SWAMPLAND conjectures are not satisfied. So from this point of view now, a quintessence in the tail with this, at least this kind of runaway potential, which seems to me the simplest one that you can have in a stringy setup, it doesn't work. It violates these conditions, the SWAMPLAND conjectures.
May I ask the following? So the SWAMPLAND conditions, in principle, are a consequence of string theory or whatever. So you seem to have derived this and suddenly find a configuration that violates the SWAMPLAND.
No, that means I cannot have quintessence in the tail. That's the only thing. So if there is quintessence, it won't be in the tail.
What would happen? Suddenly the field is rolling and says, oh my God, I'm violating the SWAMPLAND condition. Stop.
No, that means that will not, so that means you cannot source dark energy at the tail. And in terms, there are other things that will happen, but in terms of sourcing dark energy, no, that was not going to happen, okay? However, at the hilltop, this parameter goes like this, so here we see clearly that phi will remain indeed frozen as soon as Hubble friction dominates. And at the hilltop for this particular, did I give the parameters already? I think so, don't remember. Okay, but for this kind of potential, you can check, this depends only on alpha, actually on the parameter alpha, and at the maximum, this kind of potential satisfies the de Sitter conjecture because this second one is satisfied, so you don't care about the other one. So where the promising point where you may have suitable quintessence model will be at the hilltop. But of course, okay, you don't want to fall to the wrong side too early. In the future, yes, maybe. But you may also want to be able to distinguish. So if the field is exactly at the top, it is indistinguishable in principle from pure cosmological constant. But of course, something else may happen.
You are, let's say, not considering the quantum effect.
Yes, so there may be other things around. So I will mention this as well. Also, this is not just the cosmological constant. There are also the axion and the axino that will be there, and hopefully they will do some. We may be able to see something, but it's a little bit more boring if I'm there and it is indistinguishable from the cosmological constant. In principle, that's a little bit more boring, but you may want to see this and add quantum corrections as well. So, so here are the numbers. So here we see what we need in order to explain the current value for the potential, and this is derretir. Como que, yeah. Sí. Melt, sí. Melt, but thawing, yeah, it's a different word, so I don't know if there's any English-speaking person.
Thawing en castellano es más descongelar.
O descongelar, sí. Unfreeze, pero yeah. Well. So there's a specific word.
Something goes to liquid phase.
Well, they have this nice word, yeah. So maybe I don't know, that's why I say.
There's a subtle difference.
Yes.
You will explain it.
It's because of the enthalpy.
Okay. So indeed we see that we need a very specific value for this parameter A. Alpha is just, an order 1 number. And here I just plot the evolution of the canonically normalized axion.
It's almost 1 over alpha, right? Not that.
Lord.
There is some secret.
There maybe, but still, there's no secret here in A so far. Maybe there is. So here we see what happens for different initial conditions, and as you may suspect. So there is some region around the hilltop, the maximum. These regions around which you will have a successful model of this THAWING quintessence. This is a runaway position when phi initial is at, say, very large values. And in this case, we see that it is indeed indistinguishable from a cosmological constant for a long time, because eventually, of course, it will also change. It will eventually roll down. But up to when we integrate it here, it stays to omega equals to -1. So on the other hand, if you start a little bit around the maximum, you do have omega close to -1, but not quite. And this is 0 is supposed to be today. So again, what happens next is not, we don't really care. No. So we evolve from radiation, then matter, and then this is today. So we want that around today, we do have an omega equals to -1. This is what phi is doing. Essentially after today, we don't really care much of what's happening. So basically, these values we have that are still consistent with the values for the equation of states that are given by the experiments today. So if you start somewhere else, away from the maximum, this will start to change, and maybe you end up somewhere here where you don't want. Well, -1 is perfectly fine as well in principle. Mm-hmm.
Sorry, maybe it's a misdefinition of the horizontal axis variable. So n
is the number of EFOLs. Sorry.
Okay.
Yeah, sorry, I didn't. So essentially, we always we solve this with respect to number of EFOLs, even if here I put dots, which are time, but it's much easier to solve in terms of derivatives with respect to EFOLs. So then we count, which will be around, matter domination, BBN, radiation. It's approximate, roughly speaking.
And you put as an input the amount of matter and the amount of radiation we measure.
Yeah. Mm-hmm. Nothing changed there, yeah. N? The number of equals, so is the log of the scale factor. Sorry, yeah. The number of the rows? Yeah, the number, yeah, how much. This is very big. I almost cannot.
Brazilians like to have the biggest things.
Carlos, please.
Where A is the scale factor, so it's telling us how many, so it's E to, yeah. So yeah, sorry, I mean, you can always integrate in terms of time or N, and it's much easier. N is more meaningful, and it's also much short. I mean, the time doesn't have much meaning.
So any considered negative
Positive in the future, we don't care. A negative is where we started, say, BBN, radiation domination, then there's some matter domination, and today is 0, and then eventually 10 is future far away. Yeah, I mean, to me, it's always better to plot with N because, yeah.
But this is evolution of the universe, right? Nothing to do with inflation. So
It's after inflation.
dark energy, not inflation.
Yeah, you usually say. Yeah. So inflation happened somewhere in the very past. Yeah. Okay, so here is just another plot, numerical evolution of the Hubble parameter and the energy density. But okay, once we checked that indeed these parameters are good, everything else is also consistent with what we want.
Therefore, you're predicting a value of omega to be different from 1?
If you start around the tip of the, the maximum, so this is the maximum, the potential is somewhere like this. So there is a region around 4% away from the maximum, the exact maximum. You can have an equation of state omega, which is still consistent with the values of omega that are given to us by current data. If you start somewhere else, well, of course, if you start too much here, you just go too soon this side, and then here we don't, there's nothing interesting. If you start much more farther away, so this is phi. If you start farther away than, say, just 4% away from the maximum, then your omega equation of state will not be consistent with what we... Initial condition, phi initial, where we start phi initial. So we have to give initial conditions here, and that's our phi initial. Now, question will be, why did we start there? Anthropic principle, very good.
Yeah, but that thing that what prevents you going a little bit back until you got to the top?
Anthropic, because otherwise we won't be here. So that's what I wanted to say.
And remind me, probably you know the answer. TES and all these dark energy experiments, how well can they control omega?
How well they will tell us. Yeah, I don't know how much better. Yeah, in principle, how much?
It's already a few percent.
It's already a few percent. Yeah.
Yes. The equation of state.
The equation of state.
Yes.
But it will improve, right?
Yeah,
sure. Well, that's the question. So
how much is going to improve?
Can pro this model.
Yeah.
Taking this model very seriously.
No, yeah. In principle, yes.
You predict a slope in the omega parameter as a function of C.
Yeah. So this n you can translate to z. You can plot n or z. I just didn't.
Right. So that's much better. That's much worse. Because the variation of the state is much worse. fact, you have a parameterization.
Yeah.
But you can study both omega and the variation in time here in principle.
Yeah.
So you can put a dot in how.
Yeah, and see how much, how far, how. Yeah.
That ellipse that they used to show and see.
Yeah.
So you have the orange and the red. Orange is 0.5 and the red is 10.
Yeah.
And they both would keep you on -1. But
Um,
then dropping a little bit below 0.5 or just a little bit above, it seems that the green and the blue are not on the right side.
so here, I don't know what happened to this one. No, this one is, this one is just, indeed, -1. So because we are, so you are either here, this is the 0.5.
So my question is, would the orange be between the blue and green line, or it would be really with the red line?
In this plot, in this side, it's with the -1. We have to, I haven't included.
You can see orange and red there.
Yeah, it's.
Are you sure that you don't have chaoticity here? Because you're just a little bit off 0.5 and you get the blue and green, which are quite different from the orange.
Yeah, but the orange is exactly at the maximum. So it does make a big difference.
Really
It does make.
Instability there.
Yes, it's. But what we will say. So suppose we say, well, let's take this one. Today we see a cosmological constant, which is consistent, and even unfortunately I didn't plot here, but here you see what's going to happen. So eventually the field is going to roll down, and your omega will change. But
Sorry, at some point you told us that if you go to the tail,
it will look as yeah.
Then I don't understand. Again, my initial question is I don't understand what that means. So then it should mean that we should not take this seriously from the start with, because if we take it seriously, eventually we'll go to the place where it violates swamp. Right?
So what the swamplanders will tell you is that when you are there, when you are at the tail at 5:10, what I'm doing is wrong, because once I am here at 10 already, there are new states that are becoming light, and the light states are many more light states are there, and I haven't taken them into account. So so I should not be even doing this for that one. So that's where the swampland enters, saying, okay, you forgot all your states.
What part in field phases, what happened that extra light degrees of freedom enter?
So essentially, super light, and then what I did was wrong. So essentially, when the swampland is not satisfied, it's saying you did something wrong. You forgot something here or something there. So in this case, it's these light states that appear. So this indeed, I'm not sure I put it here, but this indeed is a proposal that was called fading dark matter, which again I don't find very compelling, but the idea that they propose is exactly that those light states that are appearing today, or somehow in the not so far away past, and this may explain this H0 discrepancy. But you need, again, very, I mean, it's a proposal, yeah. So indeed, okay.
That is like very dark matter, so in what sense are they different from decaying dark matter? We may not, maybe it's different, but
it's appearing.
You need to have the right injection of matter at the right time, and then disappear again. So how does it work?
No, but indeed, you're right. It has to start appearing at the right time. Otherwise, you don't. Yeah, otherwise you don't do anything. Indeed. So this point where how do you fix where the field exactly where the first state starts to appear? So no, there's no explanation for that. Oh, okay. So.
No, but I have a suggestion. We have plenty of time for discussion. So maybe even if you don't finish everything, you can continue during
Maybe I just.
I should not interrupt.
No, you should.
So yeah, okay. So this. Okay, so maybe I can just finish this part and comment on the other two things I wanted to say, and then those we discuss in the discussion. Okay, so as we were also saying, this kind of picture, well, in principle, it doesn't come, the axion doesn't come on its own. It comes with an axion and an axino. And also we were talking about, well, these sub-leading corrections. So what's going to lift the potential for the axion is sub-leading corrections. So for example, if you add an extra term to your non-perturbative superpotential like this, it has to be subleading with respect to the leading one. So we took these values for these parameters, these new parameters, and you can check that essentially nothing changes. You still can have this picture of your quintessence, Thawing quintessence. And but in this case, the mass of the axion becomes very light, so it's going to contribute to dark energy as well. So you will have two fields contributing to your dark energy. You also can look at what happens to the mass of the axino. So the fermion also gets a mass which is very light. So you may think of this as a possible dark radiation component. How exactly is all this produced will be model dependent, and you will have to check your model to see what happens. And again, I like to stress that you need a mechanism which in principle is doable for this sequestering by having the standard model somewhere in your compactification and your dark sector somewhere far away in your compactification. And in principle, you can achieve this decoupling, say, between dark energy and the standard model, sufficiently suppressed couplings. But again, all these will be questions that one will need to answer, maybe in a more complete model. So, as I said, I had a summary for each part. So here is a summary of the first part, which is the only one I did. So, okay, so I just stressed that the existence or not of metastable de Sitter vacua or cosmological constant in string theory and quantum gravity remains an open question. And but still, it is, even if we accept or not these conjectures, there are some potential possibilities to realize a quintessence in string theory, but it comes with some problems. Even if you manage to satisfy the SWAMPLAND constraints, it seems that, as we discussed, you need very fine-tuned values, but again, anthropic may be an answer to those initial conditions and those particular values for your parameters. And besides that, of course, you will need to answer model-dependent questions, such as Susy breaking and of these fit forces and the sequestering mechanisms. And of course, you are not really discussing the cosmological constant problem, which will remain as a question. So this essentially ends the part that I wanted to say, which is something more recent I have worked on. So let me just mention what I wanted to say, and then we can discuss it during the discussion session. So what I wanted to say is now, again, a scenario which, at least for the moment, is more stringy motivated, but now using some of the objects that appear in string theory, which are the brains. And this will probably be connected with something on the first talk, although I wasn't there the whole talk. So, but maybe. But the point will be that brains are interesting, or extended objects are interesting, and they may give interesting cosmology. So one of the first things you can do with this is to have a model of coupled dark energy and dark matter, which has what is called scaling solutions, in which the total equation of state goes like -1, and so you have dark matter and dark energy having essentially the same behavior. So this was something, again, that people proposed a long time ago because it may be a way to relax this coincidence problem of why is the energy density of dark energy some of the same order of matter, of that of matter. So in this picture, let me just go quickly. So the idea is to have this coupled scenario where you may have, if you look at the early universe, you can have a modified thermal dark matter paradigm. Or for late time, okay, so also people recently proposed that coupled dark matter, dark energy may be able to help with these recent cosmological puzzles. So again, these coupled models were proposed since long ago, and there are at least these two recent recent reviews, where there are thousands of references. So you can see that this is something people have been thinking about since long time ago. However, what we sort of tried to do was to have a more fundamental origin for the coupling. So this we did using D-branes. And yeah, so if I go through this, it's a bit too long, but this is the idea that once you include D-branes, these D-branes come with something that is a non-trivial coupling between matter and your scalar field, which may or may not be exactly dark energy. And this non-trivial coupling can give you different expansion rates, and in particular for late-time cosmology, can give rise to scaling solutions. So maybe I just do this later if there's space on time.
So more questions for Ivonne? Even more questions? Or we can save for discussions, no? Is it okay? So we are going to discuss this later.
Later.
Okay. Okay, so let's thank Ivonne again. And